Bismillah Rahman Rahim. Assalamu alaikum. Welcome to ASTC. This is Cambridge A Level Mathematics 9709 Mechanics. So today we will be starting off with our chapter number 2, the Constant Acceleration Formulae. So before you start, there are a couple of prerequisites here. The first one is you should be able to substitute values into a formula. So into a given formula, you should be able to substitute the values and then work out the variable. Work out the unknown variable. Then you should be able to solve linear equations, okay, simple algebra. You should be able to solve quadratic equations either by factorizing or by using the quadratic formula, okay. All right, so these are some of the prerequisites. You can take a look at some examples here as well. So this example uses factorization to solve the quadratic equation, and in this example uses the quadratic formula to solve the quadratic equation. Okay, and keeping in mind that all non-exact answers should be given to 3SF. All right, now when working with variables such as these, it is important to make distinction between scalar and vector quantities. Okay, this is the topic that we have already covered in our previous lectures. A scalar quantity only has magnitude, it only has size. Okay, it doesn't care about the direction. We don't really care where the object is moving. Either it is moving towards the right or towards the left, towards north, towards the west, and so on. We don't really care about the direction. Okay, so for example, speed does not take into account whether you're moving in a straight line or even in circular motion. However, if we talk about velocity, so even though if your speed is constant at, let's say, 20 meters per second and you're moving in circle, so your speed is the same, but the velocity is changing. It's not the same because in a circular motion your velocity keeps on changing because of the direction, since the direction keeps changing. All right, so in vector quantities, we also take into account the direction of motion as well. Excluding time, the characteristics of motion are vector quantities where the direction is equally as important as the magnitude. Okay, so for example, if we talk about displacement, that is a vector quantity. If we talk about velocity, that is a vector quantity. If we talk about acceleration, that is also a vector quantity. So we studied the differences between displacement and distance. So in order to remember it quite easily, you can say that displacement is how far an object is away from its starting position. Okay, doesn't matter, it might have traveled a lot of distances, but at the end, the point where it stops, how far is that stopping point from its starting point, that is displacement. Okay, whereas the distance, that is how much ground has been covered, that is how much area has been covered. Okay, how much length has been covered. So that's what we mean by distance. Now whether that is towards the left of your starting point, towards the right of your starting point, as I said, that distance is a scalar quantity, so it doesn't take into account the direction. We only take the magnitude. Velocity is a vector quantity which tells us how fast the body is moving and in what direction, whereas speed is a scalar quantity which tells us how fast the body is moving only. It only tells us how fast the body is moving, whereas in velocity, how fast the body is moving as well as in what direction. Now, we studied about mathematical models in our first video, which was the introduction to mechanics. So we understood some of the important concepts, like why is it important to set up a mathematical model and how it can help us in understanding the real life situations, and how the real life situations, okay, once we collect the data, how we can also improve our model so we are able to make better predictions or do better calculations. Okay, so the first part of setting up a mathematical model is to make some assumptions that will help us in simplifying the scenario. Okay, so what could be those assumptions? Like we can say that a resistance can be ignored, or we can say that our object can be modeled as a particle, as a single point, so that if we don't take into account the dimensions of the object, then we can also assume subsequently that the a resistance is not acting on it. Okay. Then defining the variables. When we say defining the variables, it could have some abstract meaning, but what we mean over here is you list down what values you know and what values are unknown. Okay, so if we talk about a situation where a car is moving, you might know that what is the initial speed of the car. You might know that when the brakes are applied, what might be the final velocity of the car. If it ultimately stops, then that will be zero. You might know that, okay, how much time it takes for the car to stop moving. So you know all of these factors, right? So you know all of these variables. But what you do not know is the acceleration, or in this case, the deceleration, and the displacement, the distance that was covered while the car was decelerating. So so there are two unknown variables and there are three known variables. Okay, so you list them down. After that, you set up the equation. Now we're going to learn how to apply this in our practice questions, okay, in a while. So basically, based on what variables are given to us and what do we need to find, we now select the equation which is the most appropriate one to be applicable in this case. Okay. Now, in this chapter, the mathematical model that we consider is the object is modeled as a single particle with no dimensions so that air resistance can be ignored. And the second assumption that we can have is that the particle moves in a straight line with constant acceleration. So we are only considering motion in a straight line. There is no motion, there is no circular motion involved, okay, in our mechanics. So basically, we'll be only dealing with a straight line motion. Now, that straight line motion could be horizontal or it could also be vertical. All right. Now, let's just go a bit deep into the concept of where the equations of motion are derived from. Okay. So let's imagine that there's a roller coaster ride. Okay. And at some points you'll notice that the velocity keeps on changing, right? So let's say that if you're going downhill, then the velocity all increases all of a sudden. Okay, assuming that at this particular point the acceleration is the same. So this is the graph that we get. Initially the car was traveling at 4 meters per second, and then at this point in 10 seconds, okay, the velocity of the car increased to 24 meters per second. So now it says that the velocity time graph in figure 2.2 shows part of the motion of a car on a fairground ride as it picks up the speed. The graph is a straight line, so the velocity increases at a constant rate, and the car has a constant acceleration that is equal to the gradient of the graph. So, even in IGCSE mathematics as well as in O level mathematics, we studied that the velocity time graph or the speed time graph, okay, if you have a speed time graph, the gradient of that graph is going to give you the acceleration. Okay, so if I select these 2 points 0 4 and 10 24, so I can work out the gradient of this line and that gradient will be equal to the acceleration. Okay, so if you apply the formula m equals to y2 minus y1 over x2 minus x1, then we can find out that our acceleration is 2 meters per second squared. Okay, in general the initial velocity is u meters per second. Now if I just make a graph with general variables, okay, so this is my initial velocity u, this is my final velocity v. The change in y, okay, that will be v minus u, and the change in time will be t minus 0. Okay, so we can write this down as v minus u over t minus 0, which is actually t, and that is equal to a. Now if I just rearrange this equation, then I will end up with this equation, v equals to u plus at. This is the first equation of motion that we derive. And how do we derive it? We derive it from the gradient of the velocity time graph. So to derive equation 1, we consider the gradient of the graph. All right. Next one. To derive equation number 2, okay, we consider the area under the graph. So if let's say I have the same diagram over here, if I want to find out what is the area under the graph, so you can see clearly that this is a trapezium. Okay, so what we can do is we can just calculate the area of trapezium, right? So that will be half into sum of parallel sides multiplied by the distance between them. In our case, that would be the parallel sides would be from this point to this point, which is u, and from this point all the way until this point, which is v. So that will be u plus v upon 2 multiplied by the distance between them, which is t. Okay, so that would give us the second equation of motion. So if let's say that if I consider the original graph which was given over here, so if I want to find out the actual distance, so I'm just going to apply the formula for area of trapezium. So that would be 4 plus 24 divided by 2. Okay, so S is equal to half times 4 plus 24 multiplied by 10. Oops, my bad. So that's what we have here as well. Okay, so the distance would be 140 meters. So in general, this is the formula. Okay, and you can rearrange it in this form. So you can see this is exactly the same as the area of trapezium, isn't it? Half times a plus b multiplied by h. That is your second equation of motion. So the first two equations of motion, which is v equals u plus at and s is equal to half u plus v times t. Both of these can be derived from the graphs of velocity time graph. Now from the graph we have derived two important formulae. If we eliminate v from equations 1 and 2, we obtain this. So if let's say that within this equation, if I substitute this v equals to u plus at. So if this is what I substitute over here, okay, now after simplification, what would I get? This will be half into 2u plus at multiplied by t. So in short, this is actually half t times 2u plus at. And when you multiply them, you would end up with this equation. S is equal to ut plus half at squared. Okay. And I'll come in a bit that why do we need so many equations? Okay. So this is equation number 3. Now, if we eliminate t from equations 1 and 2, so again from 1 and 2, if you make t the subject of the formula and substitute into this, like for example, in this equation, this is the original equation. If I make t the subject, that would be v minus u upon a. So in place of t, you substitute this portion, this expression. So that this is how it is, how it has been substituted over here. Now this 2 and this a, they both can be multiplied to the other side. So you would end up with 2as. Okay, let me write it with this pen. 2as is equal to u plus v times v minus u. Okay, if I just slightly rearrange this, v plus u times v minus u. So you would notice that this is the expanded form of a square minus b square, which is equal to a plus b times a minus b, the algebraic identity that we have studied back in IGCSEs and O levels. So that means that this can be written as v squared minus u squared. Okay, now this u squared could be shifted to the other side and you will end up with the fourth equation. All right. So now these are our 4 equations of motion. So you might have seen the equations 1 to 4 before. If you have studied physics, A-level physics, or if you are studying A-level physics, then definitely you might have come across these equations or you will come across in future. Okay. Then it says that they are sometimes called the SUVAT equations or SUVAT formulae, and they can be used whenever an object can be assumed to be moving with constant acceleration. Now, bear in mind that these equations are only applicable when the acceleration is constant. Okay, so you cannot apply these equations if the acceleration is changing over time or if it is not constant. Okay, so keep this in mind. So whenever you have a question given in an exam paper, always look for the words, whether it is saying that accelerate that velocity is increasing at a constant rate, or if it's or if it just says outright that acceleration is constant. Okay, then perfectly fine. You can use these equations. Okay. When solving problems, it is important to remember the requirement for constant acceleration and also to remember to specify positive and negative directions clearly. Now, the conventional way is that we assign right hand side and upwards as positive and left hand side and downwards as negative. But depending on the situation, maybe if my object is already moving towards the left, okay, then in that case, instead of putting everything as negative, why not consider the left direction as my positive? That would actually allow me to keep my displacement as positive. That would allow me to keep my velocity as positive, and that would allow me to keep my acceleration positive as well. Okay, so it all depends on what the type of question is. All right, so again, it mentions the same thing over here as well, that from these two equations we derive the next three equations. Actually, there's also a fifth one and we'll see that in a bit. So basically, why are they called SUVAT? Because if you notice over here, you write them in this manner. Okay, this is SUVAT, and each one of these variables, they represent these variables. Okay, each of these letters, they represent these variables. So S equals to displacement, U is initial velocity, V is final velocity, A is acceleration, and T is time. Now these are a total of 5 equations. Now we have studied until number 4. How do we derive equation number 5? Let's look that here as well. We can derive equation 5 from equation 1 and 4. Okay, so equation 5 can be derived from 1 and 4. Okay, what is 1 and 4? 1 is V equals U plus AT, and number 4 is S is equal to UT plus half AT squared. So let's write them down here. Now, if I make U the subject of the formula and I substitute this U with, with this expression, so what I'm going to get here will be S is equal to V minus AT times T plus half AT squared. After simplification, we would get Vt minus AT square plus half AT square. So minus AT square plus half AT square, that gives us minus half AT square, and thus you get the equation number 5. Okay. Now let's come to the reason as why we need so many equations. Because if you notice over here, depending on what the question is, let's say if I consider this one, where will this equation be applicable? So if I write down SUVAT, okay, so you're always going to see what variables are given and what variables are not given. Okay, so let's say that in the question I need to find V. So V, there goes my question mark. The question mark tells you that okay, this is what I need to find. Okay, you have been given an initial velocity, you have been given an acceleration, and you have been given time, but there is no discussion about displacement. So that means I need to look for an equation that has all of these 4 variables. So the only equation that has all 4 of these variables is the first one. Okay, all right, let's consider the second case. Let's say that now the variable that I don't have and I don't need to find is acceleration. Okay, I don't have it in the question and I am not asked to calculate it as well. So that means acceleration is not required. Okay, let's say I need to find time, for example, and S is given, U is given, V is given. So now in this particular case, I'll be able to use this equation. Okay, because it has S, it has U, it has V, and I can find my T. Just make t the subject of the formula, you'll be able to find that out. Okay. Similarly, if we come to equation number 3, so I hope that now you get the idea. Now for equation number 3, if you don't have t, okay, if the t is not given in the question and it is not asked to calculate, that means you can use this equation. If final velocity is not required, then you can use this equation, and if initial velocity is not required, you can use this equation. Okay, so if I just write it in this one more time, over here S is not needed. Over here, A is not needed. Over here, T is not needed. Over here, V is not needed. And over here, U is not needed. So that's why you can see that depending on what the situation is, you have to use the required formula. Now, the first four of these equations are given to you in MF19, which is the formula booklet, but the fifth one is not given to you. So it is better to remember it. It's just same, almost similar to this one, except that instead of S is equal to UT, you have VT, and instead of a positive sign, you have a minus. You have a negative sign. Okay. All right. So let's look at an example. A particle passes through a point A moving at 4 meters per second and continues with a constant velocity for 8 seconds. Okay, so it passes through a point A, so that is your initial velocity. Then it continues with a constant velocity for 8 seconds. Now, if it's continuing at constant velocity, that tells you that acceleration is equal to 0. Okay, until it reaches a point B. Now, at point B, it accelerates at a constant rate for 6 seconds until it passes through a point C, moving with a velocity of 10 meters per second. So now the question is, find the distance covered from A to C. Now remember, first and foremost, what you have to do is make a sketch. Okay, just make a quick sketch, just make a diagram. Okay, so that you know what the situation is. The diagram does not have to be like really fancy or something. Just make a straight line with 3 points A, B, and C. Now what information is given to us at t is equal to 0? The particle was moving at 4 meters per second and it was moving at constant velocity until it reaches point B. So that means from A to B the acceleration is 0. Okay, now from B to C, it does not tell you what the acceleration is. Okay, but what it does tell you is that it moves for further 6 seconds, and at constant velocity it was moving for 8 seconds. So that means you have the total time. This is t equals to 0, this is t equals to 8, and 8 plus 6, that is t equals to 14. The final velocity at which it passes through point C is 10 meters per second. So this is everything that we know, and we have written all of these values in a small quick diagram. Okay, now what do we need to find? We need to find the distance covered from A to C. So I need to find from A to B and then from B to C. So this total distance. All right. Now, so before I move to, obviously I'm not going to find A to C all the way. First, I'm going to find the distance between A to B. Okay. So again, come to SUVAT equations. What is it that's given to us? Now, if you look over here, so this is what we know. Displacement is what we need to find. Initial velocity is 4, final velocity is 4, acceleration is 0, and t is equal to 8 seconds. Okay, so if acceleration is 0, okay, so isn't it good that you can use an equation that has a and that has s, because whatever is attached with a, that would simply be eliminated, right? So we can use s is equal to ut plus half at squared, where because of a this will be eliminated. So I'll be left with s is equal to ut, u is 4, t is 2, sorry, t is 8. Okay, so 4 times 8, that will be 32 meters. Or alternatively, you can use another equation as well. As I mentioned, you can use all the any equation that is applicable. Okay, because you have 4 different values given, right? and you need to find just one variable. So that's why you have a bit more variety that which equation you can select. All right, so the answer will be 32 meters. Now I need to calculate the distance between B and C. I know the initial velocity, I know the final velocity, I don't know what is the acceleration, so I'm going to cross that out, and I know the time as well. So this is what I know okay, for this situation. So I need to find the displacement. So this A can be crossed out. Now, if we look for which equation is most suitable in this case, that will be S is equal to U plus V upon 2 times T. Plug in the values, you can find the distance. Now you add them up, so that will give us 74 meters. Okay, all right. Now, part 2 is find the acceleration between B and C. Now you need to find acceleration. Again, you go back to SUVAT equations, list the values which are given to you. So we know displacement, we know initial velocity, we know final velocity, acceleration is what needs to be found, and t equals to 6 seconds. Now my suggestion is, because this displacement is what we calculated in the previous part, okay, it could be correct, it could be wrong. I mean, not in this case, but while you're doing an exam or while you are practicing yourself, okay, there's a possibility you don't know whether you have calculated it correctly or not. So it is better to use those values which are already given in the question, which is this one, and this one. So even if this was incorrect from the previous part, okay, that does not affect your answer to this part. Okay, however, if there is no other option, let's say that you are supposed to use the value from the previous part so that you can do the subsequent calculations, then obviously you have no other option. But if you do have an option, then do not use those values which you have calculated, because if those values are incorrect, then your subsequent calculations will also be incorrect. Okay, so here we can use v equals u plus at, and therefore you can get a equals to 1 meters per second square. All right, so let's take a look at this example. A car traveling at 6 meters per second accelerates at 2 meters per second square. Calculate its speed 8 seconds later. So we have U, we have A, we have T, and we need to find V. So we can use V equals U plus AT. All right, so this is the formula given, and we can work this out. Example number 2. A car initially traveling at 8 meters per second accelerates at a constant rate of 3 meters per second square until it is traveling at 17 meters per second. Find the distance traveled while accelerating. So this is your initial velocity, this is your acceleration, and this is your final velocity. Okay, V, U, A, and we need to find S. So we can use the equation V squared equals U squared plus 2AS. Okay, so this is the working for part A. V squared equals U squared plus 2AS. Make S the subject, and you can work it out as 37.5 meters. In the second part of the question, now it asks you to calculate the time taken to accelerate. So here you can see that we are not using the value, although we could use this value, okay, but just as I mentioned, that it is better to use the given values. So I have initial velocity, I have final velocity, I have acceleration. Now I need to find time. So v equals u plus at, and therefore t is equal to 3 seconds. Okay, example number 3. According to driving guidelines, the minimum braking distance for a car traveling at 20 meters per second is 30 meters. Find the deceleration of the car. Okay, so the braking distance, okay, is basically, let's say that you see a traffic signal from a distance, okay, your car is over here. So the moment you apply the brake until the point you stop, you do cover some distance, right? So let's say that you applied the brakes, and obviously the car does not immediately stop, right? Because that would be harmful, that would be dangerous. So what you do is you apply the brake slowly, but you have started to apply the brake now until the point that your car stops. So let's say this is where you applied the brake, and this is where your car has stopped. finally. Okay, so the distance between applying the brake and stopping the car, that is what we call braking distance. Okay, all right. So it says that okay, the car was traveling at 20 meters per second, and the distance, the braking distance was 30. So this is u and this is s. Find the deceleration of the car. Now realize something, you are applying brake, okay? So that means the final velocity would be zero because the car has stopped. So that means you also have a third variable given to you, but it's not given directly. So you need to get that from the question. So now you have three variables and you need to find the deceleration of the car. So we're going to write all values which are given. So s is equal to 30. Okay, u equals to 20, v equals to 0, and a is what's required. So v square equals u square plus 2as, and you will get, okay, your answer will be minus 6 2 over 3. And it's quite obvious that why you're getting it, an answer in negative, because the brakes were applied. So acceleration is going to be negative. But the question was about deceleration. So we're only going to consider the magnitude. Okay, so therefore deceleration is 6 2 upon 3. Part B is the time it would take for the car to stop. Okay, so that would be, again, S is equal to 30, U equals 20, V is 0, A is not needed, we need to find time. So here we can use the equation S equals U plus V times T divided by 2. So you can work out the value of T, which turns out to be 3 seconds. All right, let's take a look at this question. 2 points A and B are 8 meters apart and lie in the same horizontal plane. A particle passes point A with a speed of 2 meters per second in the direction of point B. So you have point A and you have point B. A particle is moving from point A all the way to point B. Okay. The particle is accelerating at a constant rate of 4 meters per second square in the direction of its motion. At the same time, a second particle is passing point B with a speed of 3 meters per second in the direction of point A. So you can imagine that there are two particles, okay, one at point A and one at point B. Both are moving towards each other at different speeds and different acceleration. The second particle is accelerating at a constant rate of 2 meters per second squared. Determine the time in seconds that has passed when the particles meet and their position when this happens. So we need to find two things. First, we need to find that what was the time in seconds at which they're going to meet. Okay, that's the first thing. Secondly, what was their position? Okay, so you need to find displacement. Okay, all right. So if I make a diagram, so this is particle 1 and this is particle 2 at points A and B, which are 8 meters apart. So P1 is moving towards B with an initial velocity of 2 meters per second, whereas particle P2 is moving towards A in opposite direction at 3 meters per second velocity. The acceleration is 4 meters per second square, and over here it is 2 meters per second square. Now, if I start to write down the values, okay, let's first write for P1. So the distance, okay, s is going to be just s because we don't know that, and we need to find that because it says you need to find their position. So that would be the displacement. Initial velocity is 2. Final velocity, we don't know that. We don't know anything about that because we don't know that at the point when they're going to meet, what will be the velocity. And acceleration is 4 meters per second squared, and t is just t. Okay. Now, also, we have assigned positive sign to particle P1 because it is moving towards the right, whereas for P2, because it is moving in the opposite direction, we also have to consider the sign, right? Now, if let's say that the particles meet over here, okay? So let me draw it over here. If let's say the particles, they meet here. So the displacement S would be from point A, right? So it will be measured from here all the way until here. So that would be S. What would this distance be? because P2 has also traveled some distance, right? So this distance would be 8 minus S, because the total distance was 8, and from here to from this point, from point A till the point that they meet, that is S. So this point would be 8 minus S. Okay, so therefore I'm going to write this as 8 minus S. But notice why there's a negative sign, because the particle is moving towards the left. This distance, this displacement was covered in the left hand side direction, so therefore this will be a minus sign. Okay, all right. Similarly, the initial velocity, that will be minus 3 meters per second, okay, because of the direction. V, we don't know. A will be minus 2 meters per second square, and T will be just T. Now, definitely T is a scalar quantity, so it's going to be exactly the same. Okay, so for time, we don't really care about the direction in which the particle is moving. Now, what we understand from here is that if I form two equations from here, okay, so let's say the equation that we can use based on what's given to us is S is equal to ut plus half at squared. Okay, so let's work this out. This will be S is equal to 2 times t plus half, a is 4 and t square. Okay, so if I simplify this, I would get S is equal to 2t plus this 2 and this 4, they cancel. So I would get 2t squared. Okay, that's my equation number 1. As for this one, again, we'll apply the same formula. So I'm going to write S is equal to, sorry. Now the displacement for this one is going to be minus. Okay, let me simplify this a bit. This becomes minus 8 plus S. So I can write this as S minus 8. Okay, so I'm going to write here S minus 8 is equal to ut, which is minus 3t plus half at squared. So this 2 cancels with this 2. So you will be left with minus 3t minus t squared, and this minus 8 goes to the other side. So this becomes plus 8. Okay, that is my second equation. Now, if I equate both the s's, okay, so I can basically, I'm solving simultaneous equation by substitution, right? So if I equate both of them, I would get 2t plus 2t squared equals minus 3t minus t squared plus 8. Okay, bring all of these elements to the left hand side. Okay, so I would be left with 3t. Okay, let me first write down t squared. So this minus t squared goes to the other side, and this becomes positive t squared, and this is already here, which is plus 2t squared. Then this plus 2t adds with this 3t. So this minus 3 goes to the other side, becomes 3t minus 8 equals to 0. 3t squared plus 5t minus 8 equals to 0. So this is now a quadratic equation. 3 times 8, that is 24. So I can use the same factors, 8 and 3. So I can write this as 3t squared minus 3t plus 8t minus 8 equals to 0. 3t can be factorized, so you would get t minus 1, plus 8 can be factorized, you would get t minus 1 equals to 0. So t minus 1, just a minute. Okay, so t minus 1 can be factorized. You will be left with 3t plus 8 equals to 0. So that means t is equal to 1, or t is equal to minus 8 over 3. So we are going to accept this. We are going to reject this. Now, so that's the first thing. Therefore, t is equal to 1 second. So after 1 second, the particles will meet. Now, at what point will they meet? So I can plug this value of t to any equation. So if I, let's say, plug this in the first equation, so from equation number 1, S is equal to, we had 2t squared plus 2t squared, sorry, 2t plus 2t squared. 2t plus 2t squared, that would be 2 times 1 plus 2 times 1 squared, that gives us 4 meters. Okay, so we can say the position of particles, the position of particles is 4 meters from point A. All right, so that is the end of this lecture. So this is one way to do it. Okay, there's another method that is given over here, so you can go through this method as well, but you will end up with the same answer. Okay, so you can take a good look at this question, maybe pause the video and work through this solution, see how it's done. Okay, but most of the working is similar to what I've done here as well. Okay, so that is the end of our first lecture of chapter number 2. In our next video, we'll be going through our second lecture, which will also be the last lecture of this chapter. Okay, so till then, take care. Assalamu alaikum.